Thank you, Mr. Dersh. Okay. Well, you could use this toy just for the seminar talk, but you cannot take it home with you, unfortunately. Okay. So I'm going to talk about three main things. Obviously, the Tower of Hanoi, the puzzle, and then mathematicians related to the puzzles, and some mathematics. So if you are into the game, you're going to be disappointed because I'm going to talk about mathematics a lot. So when you purchase this Tower of Hanoi, it comes with a little paper. In that paper, we read this thing. Oops, going to the wrong direction. Okay, here it is. I'm going to let you take a look at it.
Oh, it won't happen yet. 64.
Okay.
I'll die before that happens.
All right, so it is a popular puzzle, and here's a picture from Hands-On Museum in Mexico City. And there's quite a tower behind her. And if you see this one, so yeah, cheated the rule on that one. Yeah. So Tower of Hanoi was first introduced by Monsieur Claus, Mr. Claus, in 1883. And the game has manufactured in several different names, such as the Tower of Brahma, Hindu Pyramid of Puzzle, Tower of Trouble. Okay. And Monsieur Claus made up the story that we just read to go with the Tower of Hanoi. So who is Monsieur Claus? It is actually a French mathematician named by François-Edouard Anatole Lucas. Here's a picture of him there. He introduced the Tower of Hanoi using Monsieur Claus, but the actual name is Lucas. And Claus is a permutation of Lucas. Lucas is best known for number theory, studied the Fibonacci sequence, and then made up his own sequence called the Lucas sequence. And the difference between those two sequences, not much, actually. Fibonacci, let me see if I can find the one that works. I should have practiced first, I guess. Fibonacci sequence has a formula f sub n equal to f sub n minus 1 plus f sub n minus 2 for n greater than or equal to 3. And Lucas' sequence has also similar formula, L sub n equal to L sub n minus 1 plus L sub n minus 2 for n greater than or equal to 3. So what's the difference? Initial. F sub 1 is equal to 1, F sub 2 is equal to 1 for the Fibonacci sequence. But Lucas sequence, L sub 1 equal to 1, L sub 2 is equal to 3. So that's the only difference, but we get different sequence of numbers, obviously, using those. He used this Lucas sequence to testing the prime numbers. And he eventually proved that Mersenne number 2 to the 127th power minus 1 is actually a prime number using the Mersenne sequence. Why is that important? Because if we have this number to be prime number, we have a perfect number also. As soon as you have Mersenne prime, we have perfect number. Okay? And that number happened to be the largest prime number discovered without using computers. Since then, all of the prime numbers discovered is using computers. He also wrote the 4 volumes on recreation mathematics. So we read this. Day and night unceasingly the priest transferred the disk from one diamond needle to another according to the fixed and immutable law of Brahma, which required that he must place one disk, or this disk, on a needle so that there is no smaller disk below it. Okay, so that means that we have the following objectives for the puzzle, meaning you could move one disk at a time, never put the larger disk on top of the smaller disk, and finally transfer all of the disk onto the other. All of the disk from one needle to another needle. Okay. Okay, that's the objective. And then we see this at the bottom. When the 64 disks have been just transferred from one needle to the other needle, tower temple will crumble into dust, and with a thunderclap, the world will vanish. Sounds absurd, is it? So, let me ask you this question. I know at least one person knows the answer to this one, but I'm going to ask this. Which of the following is the largest? A, the age of the universe in seconds. B, number of stars in the universe. C, number of ways to arrange a deck of cards. D, number of moves required to transfer 64 disks from a needle to another needle. Any guesses? You're going to go to the D? Okay. All right. Which one do you think is the smallest then? C is the smallest, you think? Okay. And the answer is? Oh, later. All right. So we're going to talk about the mathematics first. Suppose instead of 64 disks, suppose there are n disks. And the question is, what is the minimum number of moves required to transfer disk from one needle to another needle? Okay? We're going to denote that with m sub n. Well, in order to do that, we have to, here I have only 7 of them, and you also have 7. In order to move the whole thing, first I have to move the top 6 disks. In this case, we need to move top n minus 1 disks. How many moves? We don't know, but let's call that m sub n minus 1 moves. Okay, once I have moved that, then I can move the one move to move the largest one. And then I'm going to put back this on top of that one. And how many moves does it take? M sub n minus 1 again. Okay? So now let's add those numbers. M sub n minus 1 to take out the top n minus 1 disks. Put it back, m sub n minus 1, and the largest one takes only 1. And so here is recurrence relations, adding that. First, well, if you have only one disk, obviously you need only one moved. Okay. Well, think about that is if you wanted to compute the 64 with this recurrence relation, you have to go through the 1, 2, 3, all the way to 63. So the question is there some nice formula that we can use to find out the number directly? Okay, so look at this one. Recurrence relation and Claus formula. Okay? Well, m sub 2 then is twice the previous one plus 1. But what's the previous number? 1. We get 2 plus 1. Instead of adding those 2 plus 1, I'm going to keep it at that way. So m sub 3 is using the recurrence relation is 2 times the previous plus 1. But what is the m sub 2? It's 2 plus 1. Substitute that in. Distribute number with a 2. We get this. How about m sub 4? 2 times the m sub 3 plus 1. M sub 3 is this. Distribute with a 2. And then add 1. Do you see the pattern going on now? Okay. And one important thing I want you to know at this moment is this is the number of disks. And here is the sum with the largest exponent is 4. So in general, m sub n looks like this then. There are n disks. Largest exponent will be 1 less than that. And keep on adding all the way down to 1. Well, can we add that? Yes. Here's a nice algebra formula. X to the n minus 1, x to the n minus 2, all the way down to 1 is a very simple formula. Or another way to look at this is a sum of the geometric sequence. And the formula is this one right there. Well, in our case, the x is 2. So substitute the 2 in this. We get formula 2 to the n minus 1 over 2 minus 1, or simply 2 to the n minus 1. That's our Claus formula. Which means we can figure out the number of moves for any number of disks very quickly now. So if we have 64 disks, plug it in 64. 2 to the 64 minus 1 is? Here it is. 1.845 times 10 to the 19 moves. Yeah. And thank goodness we only have 7 disks.
If we stacked all of ours together.
Yeah. So let's go back and answer this. Which one was the largest? Well, we already figured out the last one is the 2 to the 64 minus 1. Okay. Age of the universe, scientists believe that it's about around 13.82 billion years. Multiplied by 365.25, including leap years. Multiply 24, 60, 60. We get that. So this number is about 42 times larger than. So if someone started the puzzle in the beginning of the time, that puzzle is not finished yet. How about the number of stars? Scientists believe that there are about 100 billion stars in the Milky Way. That's one galaxy. And there are also 10 trillion galaxies. Multiplying them, about, this is just the estimations, 10 to the 24 stars. Okay, someone said that the C is the smallest number, right? Okay, and the number of ways to arrange a deck of cards is actually 52 factorial. And here is the number. This is the largest one, actually. In fact, if we multiply all of these 3 numbers, it's smaller than part C.
So if you're losing out poker, you say, I'm going to deal now.
Yes.
I'm going to deal it my way.
That's right. Okay, so you saw this picture. There are 32 disks. So in order to move that 32 disks from one needle to another one, it will take 2 to the 32 minus 1. And that many moves. So if we think of that as seconds, it will take 136 years. Actually,
Unless you distract you in the middle of that.
right. You cannot go bathroom. You cannot go to sleep. All right. All right, so that's the introduction to the Tower of Hanoi. I wanted to introduce another mathematician, famous mathematician named by William Rowan Hamilton. He is an Irish mathematician. And this is a perfect picture of with stamps. There are two things you see in these stamps. One of them is the equations, and the other one is the diagram. Okay. William Rowan Hamilton made a contribution to the abstract algebra. Well, he first started with optics and dynamics, and after that, he was thinking about the abstract algebra. In 1843, Hamilton discovered what we call quaternion, a non-commutative group. Very fascinating mathematics. And besides this equation, you see this diagram, right? Pentagonal-shaped diagram. 1857, Hamilton introduced the Icosian game. So what is the Icosian game? Here it is. That diagram is actually two-dimensional drawing of dodecahedron, like this one. Okay, and basically there are 20 packs, and put those packs sequentially, and must start from one pack and go around all of the 20 vertices and come back to where it started from. Okay, so here's a he sold this game idea to a game dealer for 25 pounds in 1800s. Sounds like it's not that much, but I would imagine it's inflation's everything, somewhere around maybe 50,000 pounds now, maybe, I don't know. And the dealers sold the game with several different names, and here's another name. Okay, here we go. A Voyage Around the World. Puzzle consists of wooden dodecahedron, as you can see, although the bottom is rather flat, wide flat there. With a pack at each vertex of the dodecahedron and the string. 20 vertices were labeled with the different cities, and with the string, going through all of the 20 vertices exactly once. Another name they used is traveler's dodecahedron. Okay. The object of the puzzle was to start at a city, one city, travel along the edges of the dodecahedron, visiting each other city exactly once, and get back to the home, starting where it started. Okay. Well, turned out that apparently the game didn't sell well. So it was good for Hamilton. He got the money, but the game producer, game manufacturer lost money because the game didn't sell well. Yeah. However, so Hamilton is not famous for inventing this game. He's famous for this idea right here, visiting each of the other 19 cities exactly once and back to where it started from. In graph theory, we call that a Hamiltonian cycle. And then there's a Hamiltonian path to go with that. Okay. So Hamiltonian cycle is in a graph is the cycle that contains every vertex of the graph turned out to be exactly once and go back to where it started from. Hamiltonian path, on the other hand, you start at one vertex and end at the other vertex. You do not have to go back to where you started from. Okay. So here is a Hamiltonian cycle on this graph. Go this way and come back to where you started from. Okay. There's a Hamiltonian path on the second graph there. So solution to that Icosian game, this might be one possible solution, finding a Hamiltonian cycle. Visiting every vertex exactly once and come back to where it started. That's one possibility. I happen to draw that, but there's several other ones. Okay. If a graph has a Hamiltonian cycle, then it contains a Hamiltonian path. Okay, well, conversely is not true. We could go through this vertex and end at there. So it has Hamiltonian path, but it cannot go back to where it started from on this one. Well, if you wanted to do, you have to go through this vertex. And that means that this vertex is visited twice, actually. Okay. Second graph does not have any Hamiltonian cycle nor Hamiltonian path to go with that. Okay. No matter how much we try, just cannot find that one. All right. Now I'm going to introduce another class of graph called the n-cube graph or hypercube graph. So what is an n-cube graph? Well, it is defined recursively. Q sub n equal to Q sub n minus 1 times Q sub 1, or Q sub 1 is the same as a K2. Now, this is kind of fancy thing in graph theory, but simply put, basically, in order to obtain the next cube graph, draw the 2 copies of previous one, and then join the corresponding vertices. Okay, so here is, this is Q1. In order to obtain the Q2, draw the 2 copies of previous one, and join the corresponding edges, vertices. How about Q3? 2 copies of Q2, and join the corresponding vertices. Okay. Q4, 2 copies of Q3, and join the corresponding vertices. This is an ordinary called a cube, and that's called a hypercube graph. Right there. Okay. And more. And it's going to get complicated very quickly, as you can see. Okay. So why are we talking about this? Well, it turns out that every cube graph has a Hamiltonian path in it. So here's one of them. Q2 has a Hamiltonian path, sideways, and start over here, visit here, there, and come back. Okay. Cube 3, start here, go up, come back. Now let's count the number of different colors of the edges for a moment. 1 red, 2 yellow, 4, that's 1, 2, and 4. Well, let's look at this one. Starting here, go through the same as before, cross over with a green edge, and now go back to the end here. This one, 1 green, 2 red, 4 yellow, 8 blue. Do you see the connection between here and the number that we saw before? Okay. So, 1956, Crow, he's a professor at the University of Michigan, apparently. He wrote a paper on connecting n-cube graph and the Tower of Hanoi. He says, the sequence of n tuples in H sub n sequence describes a H circuit of the n-cube. What? Translation, please. Okay, here is basically means. He called it H circuit, but this is actually Hamiltonian cycle. So he said, Hamiltonian cycle in the n-cube graph describes the sequence of moves for n disks in Tower of Hanoi. Okay. So basically what that means, as we walk along the edges of a Hamiltonian path in the n-cube graph, move depending on what color of the edge is. Now I purposely colored it this way. Horizontal edge is blue, represents the disk number 1. 45-degree angle edge is disk number 2. Vertical edge, which is red, disk number 3, and the green, about 150-degree angle edge, represents the disk number 4 or green edge. Okay, so let's start. Okay, ready to play the game now? Or puzzle? Let's start with the easy one. One disk. Blue one. Yay. Okay. So if you have 2 disks, the sequence of moves should be disk 1, disk 2, and disk 1. Okay. Disk 1, disk 2, and then disk 1. Okay. All right. It's going to get complicated very fast, though. Here we go. 3 disks. Let's follow them, right? 1, 2, 1, 3, 1, 2, 1. Yeah. Okay, so 1, 2, 1, 3, 1, 2, 1. Did you get lost? Did I go too fast on you? Okay, try again. We got plenty enough time to do this thing, so okay. Start again. 1, 2, 1, 3. Okay, now 1, 2. No, yeah, that's right. And then 1. Got it? All right. Let's go with the 4 disks then. So here it is. Ready to follow this? You can do it. Maybe I'll go slowly. No. 1, 2, 1, 3, 3. Okay? 1. Oops. 2. 1. 4. That's the largest disk. 1. 2. 1. 3. 1. 2. And 1.
Well, even an odd thing I find helps when you're,
Okay,
you're sitting there.
now here is, folks. I don't have the diagram for the cube 5 because it's going to get too complicated. But you understand what's going on. Or you have to use this one to unload and then move the largest one, disk number 5, and then use same graph to move it back. Make sense? Okay, I'm going to let you try. Okay.
Makes sense.
Have you finished all 7 of them, maybe?
Oh, you got it. Nice to go.
Yeah. I'm going to illustrate with ice cream cone. When you order ice cream with ice cream cone, well, obviously the important part is the ice cream rather than the cone. So cone is just a vehicle for carrying ice creams. And I look at the Tower of Hanoi as a vehicle for talk about mathematics. So mathematics is a delicious, yummy part of this whole thing. Yeah. And some of the mathematics we talked about today might be just a call out. Number theory, combinatorics, abstract algebra, recurrence relations, Hamiltonian path, Hamiltonian cycle, hyper n-cube graphs. Those are the yummy part of this whole thing. So. And applications of this Tower of Hanoi and the, some of the mathematics might be used in data structure and algorithms, computer science. There is times when there's a little thing. FILO. How many of you heard of FILO? First in, last out. Well, yeah, data structures. So if you have the largest disk is at the bottom, that will be the last one out. And there are several algorithms have to go through before it takes that out. And also, Hamiltonian cycle is quite useful in the optimization problem called the traveling salesman problem. In that, actually, it's not the dodecahedron, but it is a complete graph. And so we are looking at what is the most economical way to go travel different cities and come back to where you started from. Okay, there's a lot of research is going on there. One. In 1998, Adamant made a connection between DNA and also Hamiltonian path on that one. So there's an application there. And finally, Hamiltonian cycle is applied in the gray codes and coding theory also. So with that, have fun and enjoy the puzzles, everyone. Thank you. Thank you.